like the last one, really cool. I like that much as well.
So all that's doing,
That absolute unit back to that card.
and this is, again, certainly more sophisticated ways they're going to end up doing this. All they're doing is bending light around. And as we talked about before, we always perceive things as if light's coming along a straight line source. If we can get light to bend around, we can get things to show up like that. So basically all that's doing is that light's coming through these lenses. There's a spot here where the light rays focus way down, then they'll come back out like this, and eventually, if it's set up right, be back parallel, so there's no magnification. And as long as something is right in this area right here, you can't see it. You can't see anything outside of here. So all I did for this is I just poked a little hole in there. So as long as that light went through this little hole, it's as if you couldn't see anything else. So again, just taking advantage of the fact that we can bend light around, but from a perception standpoint, we can't tell what's something there. So anyway, watch for that over the next bunch of years as people develop this kind of technology a little bit
One
more.
of the issues I see with like cloaking devices though, like, okay, so you're bending the light around the object.
Yep, that's one way to do it.
But the issue I have with that is, in order to do that on a person, you have to be, in order to see yourself, you have to have some light coming to your eyes.
Sure, this stuff behind it.
Yeah, but if there's.
So
if
let's
all
say
light
this
comes-
is the person right here. What you're seeing is the stuff back here that comes around. And so it's this stuff, you'll get an image of it as that light comes to you. So take a look at it. You look online, they show some examples of kind of early versions of this sort of
So
thing.
there are ways to bypass that issue of being able to keep people from seeing you while still being able to
Oh, yeah.
see yourself.
Oh, yeah.
Huh.
Put some sheets of paper out there for you. What I'd like you to do is make 2 little spots on the page, about this big, about that far apart. There's some blank sheets of paper out there for you. Oh, yeah, a little, I don't know, about a palm width apart or so.
Is that close enough, farther, far enough?
Well, we'll see. Might be a little far.
We'll see.
So,
Excellent.
yeah, about like a hand's width apart.
Good.
Just little spots. 2 little spots. Oh, just little spots. Again, spots about that area. So, little bit of spots right there.
What was your second word that you guys did?
You guys like to make your spots pretty wide, don't you?
Not the wide.
If it doesn't work, we'll redo them. How's that?
It's like just as much as, it's like just what you did.
Looking at that? Not thumb to pinky. How many of you actually have done what we're about to do with your eyes in these 2 spots? All right, here's what you're gonna do. You're gonna cover one eye and look at the opposite side spot. So if it's your right eye that's open, you're gonna look at the left spot. And as you're looking at that opposite side spot, move the page in and out and see if you find a location where the other spot disappears.
My eyes are too good.
Round it.
Oh.
Anybody getting that to happen?
Yeah.
So you're looking at one spot and the other spot will disappear. If you're in another distance.
This will disappear.
Found it.
Oh, wait.
How
I'll
many
put
did
that
not
wrong
get that?
dot to start.
Everyone get that? How come it disappeared?
For the phobias and calluses.
Woo, listen to these biology people. How come it disappeared?
There's the one spot in the back of your eye. It's like,
So how do you even get an image? As you see, you have to have that image cast onto your retina, and you've got receptors back there, but what was
Everywhere
happening?
Except for where the optic nerve
Yep,
connects.
that's where the image of that other spot hit the location on your retina where your optic nerve is, where you have no receptors. Or, as you said, your blind spot. How come then you aren't walking around with two like blind spots all the time?
Our brain is,
On the side of your face to compensate.
Even one eye.
our brain is.
If you walk around like this, you still aren't walking around with like one blank spot that you're like always being bugged by.
Our brain is very, very good at filling in gaps in missing information. It can take incomplete information and extrapolate it from there.
Yep, your brain knows that's back there. And notice when that spot disappeared, what did you see over there? It was white, wasn't it? Your brain says, hey, there's white around my blind spot, so I'm just gonna fill in whatever was around it. And so it looked white. So yeah, your brain actually processes that and fills it in. So that's why you don't have like two black spots in your vision. If you're looking at that orange wall back there, your brain fills that blank spot in with the orange. So you don't actually see that. That's one way to find out where it is in your vision. But your brain's actually pretty sneaky about how it's processing that information that gets into these little detectors here that all but one of you have two good working ones.
I wasn't making that. I'm used to it now.
Don't even know it's getting busted on. So let's talk a little bit about vision and how this works, and then we get an understanding of how your eyes work. Then we can talk about what most of you are probably dealing with is if your vision's not the way it should be, how do you correct for it? Anybody in here not wear any kind of corrective lenses? Oh, right. I do have some good eyes in here. Very nice. Okay, let me draw a little sketch here and let's see what you guys learned in biology. Let's try it just with that. So that's supposed to be an eye, by the way.
I think your pilot was pretty good.
Let's start back here. What's this thing coming out the back? That's the optic nerve. What's this stuff all back here? It starts, let's do it this way. It starts with an arm. That's your retina. We'll get some more details here in a second. Let's do the cool stuff here. What's this piece here? That's the lens. What's this here? So far, so good. What's inside here? We'll get tougher. Oh, what was that?
The opiate tumor.
Wow. Doesn't look right for some reason. Yes. Want to go for one more?
Vitreous
put some physicsy stuff on here then.
Um,
So outside the eye, of course, we've got air. The cornea has an index refraction of about that. The aqueous humor, it's essentially water. The lens, about 1.41. Vitreous humor, again, mostly water. So again, these are the indices of refraction for all of these. So, where is most of the focusing coming from? What's doing most of the focusing? It's not the lens. What's going to cause our light rays to bend so that they're not just going straight through? So here comes our parallel light rays from something. And to be able to see that, we need to focus them onto the retina to form an image back there. So where's most of that happening? Why is it at the cornea?
Is it because it's the biggest difference?
Yep. Notice that's the biggest difference in index of refraction across an interface of all those pieces. And like we saw with just simple cases like this, where you have an interface and here's light coming in. Here's that normal line, it's going to bend like this. Remember, the amount of bending you're going to get depends on the difference in the index of refraction across that interface. Again, where's the biggest difference? It's from 1 to 1.38, as opposed to all the other ones that are actually pretty small differences. So actually most of the bending, most of the focusing is coming from the cornea. The lens does some kind of fine tuning with that. And the lens can change shape to do some fine tuning of that focus, but the majority of it's going to come from that cornea. Let's try a few more things here. Let's try this. Let's look at these two cases of people that aren't seeing quite right. Let's try first the fancy words for those. No, that's a different. We'll get to that. That was a fancy word, though. We'll get to astigmatism.
Whenever you're citing this as myopia,
What's the other one? That was pretty good, by the way. If I spot you that. Spot you that. Yeah. All right, so what are these two cases? If we understand what these cases are, that'll give us some insight into what kind of lenses will help correct for this. So what's happening is we're not getting a nice sharp image on the retina, so we're not getting those rays to focus where they're supposed to focus. So let's take a look here. I'm going to draw just a crude eye. So here comes some light rays in. What should happen is they should focus right back there at the retina. But for these two cases, that's what's not happening. Let's see if we can figure out which is which. And then it'll be easy to figure out how to correct them all. Anybody know, before I ask, of where each of these cases, where that light actually does focus? If it's not on the retina? Let's back up. If you're nearsighted, what can you see and what can't you see nice and crispy?
You can see near but not
Up far, I mean, not up far, up close, but
Yep.
far away.
It's exactly what it says. Nearsighted means you can see near, but things getting far away get fuzzy. Farsighted, you see things far away nice and crispy, but as you bring them in, they start to get fuzzy. So any idea of where things are focused for each of these cases? Anybody happen to know?
Is it like further in front or behind?
Which is which? But yes.
You started this before.
Then it's really easy to tell how to fix it. Because notice what's happening here, if somebody is nearsighted, is their focusing system, that cornea lens system, is focusing too much. So what kind of lens would help with that? To get those rays to cross back here so we get an image formed there, not an image trying to form right there. If those light rays are converging too much, we'll use a diverging lens. So if we stick a diverging lens out front here, then that's going to make these light rays go like this first, and then when our lens cornea system gets a hold of it, now it focuses where it's supposed to. For somebody that's farsighted, their lens cornea system can't quite focus it enough, so it's trying to cast an image back here behind the retina. So what kind of lens is going to help with that? If our eyes aren't converging the rays enough, let's give them a little boost with a converging lens. So in this case, that's going to start these guys converging so that when our eye, that cornea lens system gets that, now they'll converge where they're supposed to. And how much we're going to correct with either of these depends on, of course, where our eyes are trying to focus things. So we'll get to that here in just a bit of how to figure out what your prescription should be. Before we get to that, I thought we'd play with a couple other things here. Let me go grab a couple things as I'm going to have you do one. Anybody know about those charts over there that hung up? Like what it's called? You probably have all done something similar to those. Anyone know what that type is called? So this is all for you guys. So Dr. Lamb didn't do this stuff in one of his classes?
You did, I just don't know.
That's an old, from, I don't know, 1800s thing. Well, I go grab a couple other things out of my office and have you all check this out. So how that works is I've set it up for a distance of 20 feet, which I put a little stripe on the floor over here. So what I'm going to have you do is swing by right on the stripe, take a look at the chart and see without squinting what's the smallest line of letters that you can clearly read. So typical normal vision is 20/20 vision. If you've got 20/20 vision without squinting, you should be able to read these letters right here. If you have to bump up some rows, that means your eyes are a little worse than what's considered normal vision. If you can read down lower, then your eyes are a little bit better. And we'll talk about what that means here in just a second. For now, if you want to swing by and take a look at the chart and see, again, no squinting, which one of these you can actually clearly make out all the letters. And then remember which row it was, and we'll talk about what that means as far as this kind of terminology. I'll be back in a couple other things real quick.
I'm trying to memorize the lowest one. Like a tiny one.
Both of them go, and then just
I wasn't confused. Everyone like, think you saw me.
What'd you do?
I would like memorize the smallest one, like before I got it. So like I would feel like it too. I'm like, well, the doctor, I can read the bottom one.
Gonna try to put it out.
I think he caught on though.
How old were you?
Like, oh. I was so sly.
The bottom one is so small.
Couldn't read it.
No, I can still read 20/20. These are just for like headaches, because my eyes don't focus. They get lazy is what it is. This is a short way to put it, is my eyes get lazy and I don't get headaches. So this is to help, but it has a special
The first one is
prism
the next one, but
lens,
that's
so
all
I
I
can see
remember.
farther away than normal vision.
I did look this up. If standing on that stripe,
Wow.
this is the best you can make out.
Nice.
That means you're legally blind.
DFPO.
I couldn't even make
So
out
you
that.
want to swing by, here's a near vision version. This one, you're supposed to hold it at 16 inches away, so I don't know, it's about like this. And see if you can read the bottom line.
Keith knows
There's
about
one
it.
of those. So you can pass this around your table, hold it about 16 inches away and see if you can make out the bottom line.
Jake, how tall are you?
6'2".
Wow. Wow, how tall were your parents?
Not that tall.
Oh.
You talking about them?
How tall were your parents?
I got the one two below
Whoa, you got two below.
He's shorter, they're both shorter than him. His dad's, he doesn't
it. I don't think they're even.
I thought you said.
They're both
My
lower.
mom's like,
They're both what? What did you guys say?
No, you said they're both lower than me, like they're below you.
My mom's like 5'9".
Was there a name for the puppy yet?
How much
No,
time?
I'm kidding, I was just stating, you're waiting to be a brat. How tall are you? 5'11". I feel like I'm not that much shorter, but I am, aren't I? A little bit. Not a lot.
There's
I wanted to be 5'10", but
an
whatever.
American class. And there was a lot of people in the room. And they sat by each other, and like this one day, it was a weird.
I got it right, it's from my chair.
Like you would like across.
This is like 40 feet, honestly, it's great.
You see when I noticed the romantic like sparks going between them, and all of a sudden it's gone.
Are you
Oh.
talking? No, there was no romantic spark.
Oh,
They sat-
shut up.
They sat together.
It was more than that.
Did you not see their
They're gonna let it get used to what?
That's love.
True love.
Cal was like 27. We had a great talk about Scooby snacks yesterday. Does that mean I'm in love with him too?
Wait, have you touched either of them?
My birthday.
So I'm
touches cat.
nearsighted, so when I do this, I can read these ones up close, no problem at all. But I have a hard time getting very far down the chart
Show
there.
them your skill.
Another version of that that you'll see that's a little bit newer one, I think it's called the Logmar chart, so that's the old Snellen chart. This is the Logmar chart. I couldn't find one that was very good quality to actually print out like that one is, so I couldn't hang this one. Same concept. The only difference is, and this is the one you'll probably see more of at the eye doctor, or the kind where they like are flipping things and they get smaller. This is what they're using. The main difference, by the way, is notice that every line has the same number of letters, as opposed to 1, 2, 3, 3, 4, 5. So this one, they did the same number of letters, which is why you see it shrink down like that. So I notice a lot of times at the eye doctor, they do things where they're flipping through them, and it's going to be basically flipping through these rows. And then they'll flip through
You didn't know.
these ones, so same kind of concept, all these have the same number of letters for the close-up stuff. So, what do these numbers mean that you hear about? You have 20/20 vision, that's supposed to be normal vision. So what is that referring to as opposed to, say, 2200 vision or 2015 vision? What's that all mean?
115 means you're really done. Sounds like L mean.
If you've got 2200 vision, what does that mean? Go ahead.
something that I could read from 20 feet away, a person with perfect eyesight could read from 200 feet away.
Yep. That means you, with the 200 vision, would stand here at 20 feet like this. Whatever you can read at 20 feet, the person with the regular 20/20 vision can go all the way out to 200 feet and read that same line.
So basically just blind.
Which is legally blind. So what's 2015 mean? That you, with the 2015 vision, standing on that stripe, can read a row over there that somebody with normal vision has to move up to 15 feet to see. So if I'm standing here with my 20/20 vision, and that row I marked as 20/20 is the best I can do, for me to see the next one, I'd have to come 5 feet closer, and then, oh, no, I can read the next one down. But the person with the 2015 vision can still see it from that way. So that's what this is referring to. So again, somebody at 20 feet can see something that people with normal vision see at 15 feet. So if normal good vision in the United States is 20/20, what is it in Europe? A Royale with cheese? What is it? What would it be in Europe?
I just watched that movie last night.
Yeah, because they don't have quarter pounders out
Because of the metric system.
there. Yep. It's 6'6", 6 meters. So, same concept.
Oh, I thought it was like.
So, let's see what else we can talk about. Let's try this one.
That's what they do.
So here's a little chart I found. So this one, I think it's supposed to be done at like 3 feet away, so you might have to have it out a little ways. I don't know if anyone will have this in here, but if you've got glasses on, I think you're supposed to try it without glasses. See if any of the lines are not the same. Are some darker and some more gray? If somebody can get that to work, let me know. So about 3 feet away, that's not 3 feet. About 3 feet away, see if.
That's like 3 feet, that's a lot of
Right? For real?
That's one meter.
It's like this.
That's not
Oh,
I thought you were going like
That's what-
this is 3 feet.
Yeah, interesting.
No, like, just stick it way out.
My arms are at 3, like, it's 3
This is slightly more than 3 feet, by the way.
Just do it, just stick from your forehead.
So you really see some dark and some gray. Oh, that's awesome.
You see, everybody's trying.
This is about 3 feet.
Yes.
Anybody else see some dark and gray?
like here and stuff, I guess. Do you see it?
Anyone else?
Are you supposed to look in the middle?
So are any of them
So you
different?
really did see something. Anyone know what this is supposed to be a test for?
Well, it could be either.
It is. It's an astigmatism test.
Isn't astigmatism when like your eyeball shape is not what it's supposed to be?
Might want to get checked.
It literally looks like a circle. Nothing is wrong with it. This is making me mad. That's. Now that's.
Yeah, I feel like that is pretty wrong for the.
Is something supposed to be wrong with this?
I think if you see something wrong,
Might
there's something
want to
wrong.
check.
Ah.
So this is an astigmatism test, and what happens with astigmatism is when your cornea is not spherical. No,
When you drive at night, are the lights, do the lights have lots of, like a long
Little
border
stars.
or a long street?
that can be something
Yeah.
else too.
Yeah.
But what happens is if your cornea is not spherical, then, see if we try to draw a picture. So let's say we're looking right straight into somebody's eye. So here's the cornea part. So the light's coming in like this, here's the little people right there. What that means is that because it's not perfectly spherical, your eye may be focusing different along, say, this plane or this plane, or again, that may be tipped depending on how your cornea is shaped. Which means you can't focus on horizontal and vertical lines at the same time. And so that's what that's supposed to test. So the reason you were seeing some gray stuff is your eyes were focusing in one direction but couldn't keep the other in focus with it. That can be corrected for with lenses. And the way you can do that is with cylindrical lenses. So I'll try and sketch what a cylindrical lens would look like. But it's basically take a tube and slice it in half, like the long way, and that would be a cylindrical lens. Or I'm going to try and draw a couple pictures here. So it'd look kind of like that, where here's the bottom part of the tube here. So what happens with a cylindrical lens compared to a regular lens, so here's a regular one. Just notice with a regular spherical lens, you've got one high spot right there. With a cylindrical lens, you've got a high spot that goes all along here. So notice that if I look at some light that's coming down in the plane of the board, like this, each of these rays is hitting a different curvature, so each is going to bend a little bit differently so I can get it to focus. Where here, each one of these rays in the plane of the board is hitting the exact same curvature. This is the high point of that cylindrical lens. So just to try and show you it more in 3D. So if I've got a lens shaped like this, any light rays coming like this are all hitting the exact same curvature. I will get focusing as they spread out in this direction because each of these rays is hitting a different curvature. So I do get focusing this way, but no focusing this way. And so you can adjust those curvatures to take care of astigmatisms, where you're focusing where your eye is focusing one way but not the other, so to speak. A little bit like that. So anyway, get checked. Now I'm scared to give out the other one, the next one. Anyone know what this test's for? Anybody done this one before? Yeah, do this. Yeah, you don't see the figures? So this one you put says 14 inches away from your face, so pass a few of these around. Hopefully you all are too young to have to worry about this yet. But this one checks for macular degeneration. It tests different parts of the retina to make sure they're functioning properly. So I do get to see, nothing too bad, I see a few little wavy things here and there. So cover one eye, stare at the little spot and see, do all the other lines look okay? Or you see some missing pieces or some wavy pieces. Again, most of your eyes should be fine.
That was so funny. Look at him from this way. It just looks funny. I can't smile. Look at it. Oh, okay.
Are you okay on that one? Your retina's
Contact your eye doctor immediately.
If you can't see the dot.
Yes.
So you just stare at the dot, and then you see a green. Oh, these ones.
However, you're supposed to stare at it, usually.
You have to close one eye.
You'll know pretty quick.
You have to stare at it for 30 seconds and then switch the other eye.
Yeah, you'll know pretty quick.
Are you good?
I'm good at the ER right now.
So no macular degeneration? Everyone okay there?
Yeah.
So again, what that's doing is it's casting an image of that grid on your retina, and then see what kind of image you process when that gets cast back there. Just make sure different parts are working okay. So that was good. So, fair number of you do have either glasses or contacts. How many of you know what your prescription is? And are willing to share it? I understand there's like HIPAA laws and things like that, so. Are you willing to share what it is?
I'm negative 2.5 in both.
No. Oh, I'm gonna blackmail you with that information.
All I can remember is that I'm legally blind.
Anyone else know their prescription? Mine is this.
Wait, don't you teach shooting?
That's why I coach. That's why I coach. Anyone got a positive one? What do you got?
I was told if I was gonna look for more readers, that it was either a 1 or 1.5.
Plus?
Plus, yeah.
Anyone else know what theirs is? Anyone know what that means? Anyone know what the units are on that? There are units, actually. It's minus 1.5 what? There are units. In diopters. All that is it's the power of your lens, and it's pretty simple. The power in diopters is just 1 over the focal length of that lens, as long as that focal length is in meters. It's the only thing you have to watch on these. Is to get the units right, we need that focal length in meters.
So it's diopters is reciprocal meters.
Yep. And notice what this means then. So hopefully you've kind of seen this with the little lenses we were playing with, is the shorter the focal length, those were the fatter lenses, the more they were focusing things in. In other words, the stronger that lens is. This way, it's just the bigger the number, the stronger the lens. So when I see this is a stronger lens than this one is. Which gives us then a way to calculate prescriptions, because 1 over the focal length is 1 over distance to the object plus 1 over distance to the image, like we saw before. The nice thing about doing these problems where we're dealing with prescriptions, we don't have to worry about calculating this and having to flip things over, because we're not calculating focal length, we're actually calculating power, which is this directly, so there's no like inversing that once you get that answer. A few things to know about. In looking at these prescriptions and how they come up with that. Let's start with a little bit more terminology. And that's these 2 things. The near point and the far point. So what are those? So I'm nearsighted. So my issue is actually dealing with a far point. So let's see what that means. So if I pop these things off, I can read this without a problem. So what do you suppose the far point refers to? That's how far can I put this before it starts to fuzz out on me. So I've got a range. I mean, I can still see it clear as day right there. But by the time I get to you guys, you get fuzzy. So that far point is as far, or that's where I put this out there and I start to lose it. So what's a near point? So if I'm farsighted, I can see way out there. But then you see people trying to read things, and they're like holding it way out like that. So that is, see things nice and crispy way out there, how close can I come in before it starts to fuzz? And some people have issues with both. There's a range in between that they can see, but if you get too far away, it's fuzzy. You get too close, it's fuzzy. And we'll maybe mention how you actually can correct for that. So here's some things to know to get set up for doing these kinds of problems where we're trying to figure out what kind of prescription to give somebody. Is, for a particular case, we'll have to take care of where's the object that you want to see. That you can't see without your prescription lenses. So you've got some object sitting somewhere, you can't see it without your lenses, but I need to know where is that object that I want to see. And here are the conventions we're going to use. For somebody farsighted versus somebody nearsighted, where is an object going to be that they want to see, that they can't see without their lenses? Let's do the nearsighted one first. That's a little bit easier to figure out. So I pop these off. Where would I really like to be able to see things crispy, but I can't without them? How far? How do I say really far? What's it? Yeah, I want to be able to see an infinite distance away, nice and crispy. So for this case, that's how far away I want to see. I want to be able to have an object out in infinity, but be able to see it nice and crispy with my lenses. How about somebody that's farsighted? So they can see no problem out in a distance, but where's an object going to be that they can't see without their lenses that would sure be nice to see? And what's a typical example? You see this with a lot of older people. Where do they want to see things that they can't without glasses?
Zero.
Not zero, because that's pretty tough. Anyway. And there is a standard number we're going to use, but see what you guys are thinking. Where would it be nice to be able to see something? Yeah, in fact, what's the typical example? You want to read something. So if I'm farsighted, that means I can't read things, but it should be nice to be able to do that. The standard distance that's used is 25 centimeters. So again, you can see things way out there. I'd love to be able to see it right here. But I need my prescription glasses to be able to do it. So we're going to prescribe to be able to see an object here at 25 centimeters away. The next thing we have to figure out then is where should the image be formed so that we can actually see it? Again, we'll look at these two cases. For somebody that's farsighted, for somebody that's nearsighted. So we figured out, again, the standard numbers that we're going to use for where the object is going to be placed. Now we need to figure out where we need the image to form. So if you're farsighted, you want that image to be formed at the near point. In other words, that's the closest in you're able to see. So, yeah, here's what we're going to do. We're going to put an object right here. I want to use a lens to form an image out there where I can see it. So we're going to form an image out there at that near point. That way we should be able to see it. For somebody nearsighted, I've got my object way out there at infinity that's all fuzzy. I want to use a lens to form an image at my far point out here where I can see it. So let's say my far point is right here. I'm looking at something really fuzzy out there. If I can get my lens to form an image right here, I can see it nice and crystal. So with that, let's take a look at a couple examples of how you prescribe lenses, and let's see if some of this makes some sense based on things we've already done. So let's say we've got this case. We've got somebody that's farsighted. And they've got a near point of 100 centimeters. Let's prescribe some contact lenses. In other words, what we're going to do is find the power of that lens, which is 1 over the focal length, which is 1 over distance to the object, plus 1 over distance to the image. So here's what we're going to do. I'm going to be careful with how I draw this for the moment. We'll figure out what kind that's actually going to be. For now, this is just a lens. Here's the object. So again, we want an object 25 centimeters away. And where do we want the image? Out there where they can see it, right? So just be careful of this one thing. Where is that on the picture? Over here someplace. There's the near point, so that's over here someplace. So let's calculate it, see what kind of prescription this is. So that power is 1 over distance to the object. How far away are we? And looking ahead, if I want this in diopters, I need to make sure I change everything to meters. So our object is at 0.25 meters, and like we've been doing before, is it plus or minus? It's in front of the lens, just a typical case. Plus 1 over distance to the image. Where's our image? It's 100 centimeters away. I'm going to watch the units because I want my answer in diopters. So I'm 1 meter away. Plus or minus for a lens. Why is it minus? Because for a lens, the normal situation is object to the left, image to the right. This is where the refracted rays would touch the actual image. This is one of those cases where, oops, there's our image over on the other side. Almost like it's the wrong side of the lens. That's when we use that minus. That'd be a virtual image. So what do you get when you plug that into a calculator? And notice we don't have to inverse our answer. Somebody plug that in real quick. What's 1 over 0.25 minus 1 over 1? What is it?
3.
Plus or minus? Plus. And since these are in meters, this will be in diopters. What does that plus mean?
What kind of, is it conversion?
Yep, remember, that's really just figuring out a focal length. It's the inverse of the focal length, but the sign is the same. Remember, the sign on focal length told us, is it a converging or diverging lens? So what kind is this? That's a converging lens, and is that what we said before? For somebody that's farsighted? Yep, look back at your pictures. Sure enough, yep, there's the converging lens part. all of us nearsighted people, let's see how that works. So here's a nearsighted example. Let's say this person has a far point of 50 centimeters. So go about half a meter out and things start to get fuzzy. Let's prescribe a lens for this person. So that power is 1 over distance to the object plus 1 over distance to the image, which is 1 over distance to the object. Where did we say we wanted the object for somebody that's nearsighted? Where do we want to have something that we can't see, that we want to get all nice and crispy? That's where, for a nearsighted case, we're going to put our object out at infinity. Plus 1 over distance to the image. Where do we want that image? We're going to take the object out there at infinity, make an image where we can see it at this far point. It's still in front of the lens, so that turns negative. That's change that to meters, and we get that prescription. And again, what does that negative tell you? Oh, that's a diverging lens. Again, like we had talked about before. So it's a diverging lens, and the number here tells you how strong it is. Where because we didn't flip it over to get a focal length, we left it like this, the bigger that number, the stronger that lens is. The plus and minus just tell you whether it's a converging or diverging lens. So here are some converging lenses. I'm sorry, diverging lenses. Here's a converging lens. What happens if somebody can't see out far? Then they've got this little range where they can see, but now they struggle to read things up close. Then what? Yep, then you're talking bifocals. And the way bifocals are set up, anybody have them by any chance? The way that works is when you're trying to look at things in the distance, you're typically looking through this part of the lens. So this part lets you see in the distance. When you read things, you tend to look through this part of your lens. You tend to tip your eyes down to read. And so this part gets set up to look up close. So you can have different prescriptions in the tops and the bottoms. And these days, they can make them without the little lines in them. But the older ones, you actually see the little lines, you see the two different parts, but nowadays they can make them without, which actually is what these are. These are actually bifocals, which are weird to go through. Your eyes can get used to it. Any questions up to here? Let's go ahead and take a break, and then we'll talk some more eyes. All right. Before we slightly switch gears.
Which one?
Any of you happen to have had LASIK done? You guys know what it is and what it's used for? We're going to get a nice talk on that here at our little conference, by the way. So today you just get the quick version, because that's one of our topics for the conference.
Oh.
Did they just change the curvature of your cornea?
Yeah, all they're doing is changing the curvature of that cornea. So, any idea why it's used more for like people who are strongly nearsighted? Yeah, so nearsighted, we're focusing too much, it's easier to flatten a cornea, and so it doesn't focus as much. So it works pretty well for that. I think what they do, anybody know somebody that's had it done?
My dad.
Sounds horrible.
It was terrible. He was
Like, don't they like,
Video of how they do it?
oh, I don't even want to look. I've heard about it.
So, yeah,
So-
I've seen a quick video and I was like,
Tell me if this is right or wrong. I heard they like peel a flap back, and they get in there with lasers and they burn some stuff out, and then they put the flap back down. Does that sound right?
There's another one that sounds like it's even worse, but it's like permanent, like LASIK, you have to do,
way down your eye, and you're like blind for like a day or two or something like that. But it's like permanent, I guess. It's something with the, I don't know what it's called, it's like EFT or something, or?
Yeah, there's new stuff that they're doing. Again, we're gonna be getting a nice talk on this a little bit
The
later.
LASIK
so-
sounds way too invasive.
But well, I'll tell you what though, if this is the best you can do is see right here. So fortunately I can walk around like this and function, but for those that's all the further they can see, and you get up in the morning and can't find your glasses, that's probably not so fun. So for people with really strong corrections, they can actually do a pretty good job just shaping the cornea and get you back to pretty close to 20/20. Or at least down to glasses like this. So kind of cool what they do. So again, more later when we get to our conference. One way to understand some things, and for today's topic, our eyes and how we see things, is to do a comparison between different systems. So I'd like to chat just a little bit about a comparison between our eyes, that a lot of you know about from your bio classes, and eyes of deer, and how they're different. And kind of bringing out the differences, I think, sometimes helps understand a little bit better how our eyes work. So first let's talk a little bit more about human vision, then we'll switch to deer. Other than, since the advent of electricity and light bulbs, when were humans running around doing things most of the time? What part of the day or night? In the daytime. So we're designed to function in the daytime up until we had lights, and now you're students in science classes, so now you're designed to function all night. But before that, we're designed to function in the day. So our eyes, our little detectors here, were developed to help us out in the day. And there's some features of how our eyes act that help us with that. So let's dig a little bit deeper here into what's actually on that retina. So you've probably heard about that. So which is which? What does what? What are those rods and cones doing back there? In one of those, we've got different types too. Which one do we have different types of?
Cones are colored, aren't they?
Which is the colored ones? Anyone know?
Is it cones?
It is. And do you know what kind of cones you have? 3 are?
Red, green,
I'll flip them here. Oops. What's the other one?
Blue.
Yeah. We've got 3 of them. Only one kind of rod. These are for dim light vision. And they just see in black and white.
It's more about, it's not so much color as much as just intensity, right?
Which, these guys?
The rods. It
Yeah,
doesn't distinguish
yeah,
between
yeah,
different
yeah.
wavelengths, it
Yeah.
just distinguishes intensity in general.
I'm gonna try and draw a really bad rough sketch here of what those cones are doing. Is each of them sees in a different region here with some overlap. So if you add this all up, this is kind of what we end up seeing, which peaks in the neighborhood of about 555 or so nanometers. Anyone know what color that is roughly? And why our eyes might have peak sensitivity there? What's providing up until the advent of electricity and providing our light in the day. Sunlight, right? Yeah, that's yellow. That's what our sun looks like. So that's where we're designed to see best. Let's see, a few more things. Let's test your knowledge. What's that? Or for those of you who have taken medical terminology, maybe you even recognize those words.
Eyes.
Good try. This you can't fake. You have to know these.
It's the gel thing.
What's that?
Isn't it like a gel thing? Like a gel.
If I remember right, it's that spot and that's yellow.
Yeah.
It's a yellow spot on the back of your retina. And what's in the center of it? What's that thing? So that's in the center of that yellow spot. That's where your central vision comes from. And what's packed really tight in the fovea?
Cones.
It's packed full of the cones with no rods in there. So these cones are all packed nice and tight there. That's where our central vision comes from. So whatever you're looking right at, that image is being cast on that fovea where all those cones are. The things out in your peripheral vision, that's hitting other parts of your retina. One thing that's kind of interesting is in that macula lutea and even in your lens, you've got some yellow pigments. Back here, it's actually, for those who've had some chemistry, it's actually from lutein and zeaxanthin. It builds up in there, it gives you a yellow pigment. So there's some yellow pigment back there, there's some yellow pigment in your lens. Any idea why that's a good thing for us running around in the daytime? That and the combined with, we actually don't have all that many of these blue cones. So those are some good things for us. This is probably not even a good picture here, it's probably more like that. Remember we talked about chromatic aberration? If you send different wavelengths through a lens, you can have them focus at little different spots. What all this is doing is we want to see nice and sharp during the daytime. So what that's doing is it's filtering things out here in the short wavelengths to give us not quite as broad a range of real intense light that's going to help us get a little bit more of a crisp image. So how does this compare to deer? How are their eyes different? First of all, if anything I've asked all semester, you guys know this, and spearfish. One of those darn things running around.
At night.
Yeah, they tend to be out running around at night, sleeping in the day. So they need to be able to see at night. We need to see in the day, they need to see at night. So how does that change how their eyes are? One thing that's interesting is they only have 2 cones. It's like they're missing one. We have trichromatic vision, we have dichromatic vision. And if you look at those, they have a whole lot more blue cones than we do. So they've got a whole lot more of these guys that go way down lower, and here's the other ones. And so their vision is quite a bit different than ours. They've got a lot more, or a lot better vision down here in low wavelengths, even down here in the ultraviolet that we don't have. So let's see what gives them a lot better night vision than we have. Besides the fact that they only have two types of cones. One thing, very simple. How's their pupil compared to ours? It's a lot bigger. And why would that let them see better at night? More light's coming in. They just flat out have more light coming into their eye, getting back to that retina. So that one's easy. They've got a retina packed full of rods. Why is that good? Those are really good dim light detectors. Read somewhere it's almost 90% of the retina is rods, so they've got lots of really good dim light detectors compared to us. This one's sort of interesting. Where we've got lots of our cones packed in that fovea, right in our central vision, they've got them more spread out over that whole retina. And what I read about this, for us to actually focus on something, we have to look right at it and really get that image formed right at that fovea, where they don't have to like move their eyes around to focus on different things. So they, I think, my understanding is they've got a much broader way they can focus than we do. But also they've got much more of that retina then that can take in that light and give them an image with those, not just the rods, but also the blue cones that let them see in this dim light that's down here. All right, test your biology again with this next one. Somebody who should know what this is. See if I pronounce this right. The tapetum lucidum. Let me see if somebody else knows this one. Anybody? Just, you don't have to say it, just, I can see some hands. Anybody recognize that?
Do cows
I
Uh,
know cats and dogs.
Cats and dogs do, for
And
sure.
what happens if you take a picture of a cat or a dog's eyes with the flash on?
Yep.
Ooh, that weird stuff in the inside of your eye.
Or you're out at night with a flashlight,
Yeah.
or your headlights. I can't remember on cows. I don't,
I dissected a cow
Lambs
once
have-
and it had
do they?
a blue thing in the back.
How many have seen out in the dark, like eyes glowing at you?
Oh, yeah.
So what's up with that?
You know, not my eyes.
That's this thing. What is that thing?
Is that good, like a type of, or a lining on the inside of the eye?
Yep.
Where
They have a reflective layer in the back of the retina.
it looks really cool, like
Hmm.
pretty blues and purples.
Yep. There's this reflective layer back there. We don't have that. Why is a reflective layer on the back of the retina a good thing for creatures of the night? A lot of times critters that run around at night, when you put a flashlight on, you'll see their eyes shining back at you. Why is that a good thing? There's not a lot of light available, right? They need to make good use of it. Us running around the day, we've got plenty of light. At night, not so much light. If light comes in and does not get captured by a photoreceptor, they've got another chance at it, because it can hit that reflective layer, reflect off of that layer, and now has a second chance to be captured by one of those photoreceptors back there. So it makes for a lot more efficient capture of the light by giving it a chance. If it's missed the first time, bounces off there, we can catch it the second time. So you see that in a lot of night creatures. And the other thing that they, so this is something they have that we don't, something that we have and they don't, is that yellow pigment. So they don't have that yellow pigment that's chopping this off right here. So when they are running around the night, they can even access these wavelengths. So all of that stuff makes for some pretty efficient night vision. So, how many of you know, I'm sure you know this, that we can see blaze orange, but deer, I'm going to say it wrong, but you'll hear it, deer can't. They really can't see, but they don't see it as blaze orange. You guys know that, right? So what's up with that? So blaze orange, look this one up, it's up roughly around 600 nanometers. So, yeah, it's, you know, we can see that pretty well. But where does that sit for a deer? That's like in this area. It's not that they don't see it, they just don't have that red cone. They don't have a red receptor, the one that we do. So what do they see it as? Pretty much everything this direction.
Oh, they just see it as green?
Not green. Pretty yellowish. So to them, it's going to blend in with all the other things out here. You know, the greens, the reds, things like that, all sort of kind of start to look the same. So again, it's not that they don't see it. It just doesn't stand out as different colors like it does to our eyes. How do we know what it looks like to a deer? It's actually a couple ways. What was that?
Said we weren't hunting and they were on
Some trial and error till we found something? There's a couple different ways you can do this. One really sciencey way, you can take deer eyes, shine wavelengths in there and see what's absorbed, see what's reflected, and deduce things from that. So you can see which cones they have in there, and again, how it's absorbing different wavelengths, and make inferences. Here's a really cool way of it. Apparently there are some people with one trichromatic eye and one dichromatic eye. So you can ask them, this way looks like blaze orange, what's it look like through your other eye? You can just ask them what it looks like. Because they can compare them. I think it's pretty rare, but I've heard there are some people that have like a human eye and a deer eye, basically. So one trichromatic, one dichromatic eye. Yep.
Can we, if we're about to move on, can we talk for just a minute about how cephalopods see color?
How?
They only have rods, they don't have cones, but you know how they have like that weird W-shaped pupil?
Mm-hmm.
They can actually change the shape of the pupil
Mm-hmm.
so that the
Yep.
light will be focused in different parts of their eye.
Yep, so they've got, again, a very different structure.
And
So-
depending on where it's focused in the eye, they see it as a different color.
Yep, so very different function, very different way of seeing. Eyes are pretty amazing of how they work. Again, there's different creatures do some very different things. We're talking about even just different wavelengths that can be seen. Let me see if I can find a quick picture of this for you. While I'm looking this up, just one last thing on the deer. So apparently this is legit. We talked earlier about, a second here. Oops. About what happens when you throw your clothes in the wash with some good laundry detergent. It's like, ooh, my whites are whiter than white. And what they're doing is, again, we mentioned this, they're putting UV brighteners in. So you get actually UV brighteners in your clothes that are fluorescing in the ultraviolet. So we can't see that fluorescing, but it gives us this impression that things are really, really white. Guess who can see in the ultraviolet?
Deer.
Yeah, deer can. So it's possible for you to have all this nice camo and stuff on that to you looks like you're blending in, but if you've got UV brighteners in it, it's possible that you're standing out nice and bright to that deer. And they do make UV killers. I'm not exactly sure how they work, but there's stuff you can either wash your clothes in or spray on that apparently take care of that, those fluorescent brighteners. Let's see, what was I looking up here? Got sidetracked with my, what was I gonna look up for you? I was gonna find you a picture. Because you guys were all paying attention.
All you said is there's one thing about deers.
Yeah.
That's all you said.
Tell us what you're gonna look at.
Yeah.
You were really excited.
Yeah, it was really exciting. What was it?
We're talking about like cephalopods.
It was after the cephalopods. Darn it. It was really good too. I was gonna try and find you a picture of something, right? Shoot. Because it didn't have to do with deer. It was something not with deer. Help me out.
It had to do with deer.
No, I said before I get off the deer, I can mention the brighteners.
UV killers.
We'll have to replay the tape.
Actually,
We'll replay the tape. I'll show you later. How's that? I'll figure it out. It'll come to me tonight. All right. Any questions on this stuff?